Okay, want to just go over a little bit more on the week two port configuration. We had talked about that the Cube IDE generates code for us, and in general, what it does is it defines a bunch of structures that relate to the different registers because there's so many different registers, and so they have an initialization function that takes the information from your structure and goes and fills in the appropriate ones and zeros in the registers. And so, and in the GPIO, for instance, when we had the different LEDs and the buttons, then there's this GPIO init, and it's down below your while one statement in your main. And it does things like underscore HAL RCCs turning on the clocks. And when we looked at that picture of where all the buses are, it turns on the clocks all along the route in order to let data go to and from the ARM chip. And then here is us filling in, or rather the software filling in the pins that you want to operate on. In this case, I had a green, an orange, a red, and a blue pin, and then the modes, whether it's output or input or what have you, and then whether you want pull-ups or pull-downs, and whether you want it to do it quite quickly or low speed. And for instance, on an LED or on a button, we probably don't need anything too quick. So GPIO low speed. If you had faster acquisition of data that you wanted to make sure that you were going to get, you could go all the way up to 100 megahertz on some of those. And then the HAL GPIO init function, it takes the port that you're working on, and if you were just working on button or something like that, you just had one thing, then it would go, oh, well, then it would, in main.h, if you call the pin button, then it would have button GPIO port, and it would associate it with port A for the buttons case. With LED, because we had different LEDs on port D, and we had green and orange and all of that, then it doesn't know really what to call it, so it just called it port D. And so we have port D, and then we pass it the address of that structure, and then that function goes and looks at the pins and decides what ones and zeros to stick in all the appropriate registers to set up what you wanted. Okay, and you used to have to do that by yourself and go and look at all of this, and it does a lot of that for you. When we go look at ADCs and serial ports, and it does the same kind of thing. It has a structure. You fill in the structure, call the initialization function, and their API goes and sets the bits. Okay. There's also, this is the hardware abstraction layer API. There's also a few things you'll see. There's a CMSIS layer, of which the HAL API calls. There's also a bunch of drivers called LL, low-level drivers. In some cases, you could be doing things because of the layer of abstraction. There's a bunch more layers of software to get through, so it could be slower. So it does offer you the ability to speed things up by going more directly through it. It's like when Microsoft, when Windows first came out, you couldn't play games on it because there was too many software layers. So Microsoft came up with DirectX, which goes through a bunch of the layers and more directly talks to the hardware. The same kind of idea. This is good for most, but if you find that the software is sluggish in areas, we can go more close to the bare metal of the CPU. So you can, again, go to the CMSIS layer or the low-level driver layer. The closer you go down through the layers, the less abstract it is. So if you needed to change to a different micro in the families, there's more tweaking you have to do to go from one to the other. Whereas if you call the HAL layer, it's supposed to move across all the Cortex families. So from the F0 to the F4, you've initialized it. If it's port D, it'll work across the range. Okay. Now, I said on this that you had port D. And one of the things when we had port A, port B, port C, we looked at the individual registers and we said, okay, if I go back up here and look, I said that here's mode, and its address offset was 0. And then we go to the, and that's a 32-bit register, so there's 4 bytes. And the next is type. And so in this case, it says offset is 4, because we're already 4 bytes up from the previous 32-bit register. And in this case, we have a 32-bit register, but the top is reserved, and they only use the bottom bits for it. So it says here, bits 0 to 15. These bits are written to decide whether the pin is either an output push-pull or an open drain. And so it didn't need 2 bits for each one like some of the other ones in setting the different modes. Okay, but the offset was 4. And then we go to the next register, and we have the speed register, and the offset is 8. So there's a base address, and then it knows if I passed it port D, that you have mode, and then output, and then speed, and so on. Now, where all that comes in, if I have, for instance, I want to just show this one, if I can blow it up here. Can I blow it up anymore? This is a memory map of, let me see if I can. And so this is the Cortex-M3 memory map. The Cortex-M4 memory map looks just the same as far as this end of it goes. It's a 4 gig address space. It's a 32-bit address space. And so we go from our way down at our all zeros, 0, 0, 0, 0, 0, 0, all the way up to FFFF. And with the 32-bit address space, we divide up this memory map into different areas. So it's saying here all the way, all zeros to 1, all Fs, that's the range that you have to put code. Now, there's not all of that space in this chip. We have 1 meg of flash in here, but they could come up with another chip that has 2 meg or 4 meg or what have you. They've made it the same across the whole family of Cortex processors, and then said, okay, we've got lots of addresses available because we have 32 bits to be able to put things in places. After the code space, then they have a space for your RAM to be able to put all your variables and things like that in it. Again, depending on the processor, depends on how much you have in there. They also have a little area carved out that does some interesting special things I'll maybe talk about a little later on. It's called bit banding. Because they have so many addresses available, they went and said every bit in this region can have its own address. So you can directly go to 1 bit in either a port or in memory or what have you, and toggle that 1 bit. There's a direct address for each and every one of those in this little area. And same with peripherals. We have so in the peripherals, you'll have your ADCs, your GPIO ports, all of that kind of thing. So there's a whole area that we can map it in. And it starts at, so we got 3, what are we at? 40 million, right? So it starts at hex 40 million in order to have all our different peripherals. So from there, you will have port A, B, C, D, ADCs, everything else. You also have the ability then to put in external RAM. And so if I hook up to, in fact, your board will allow you to hook up an external static RAM chip or NAND chip or TFT display in a not just interface with SPI. Your current TFTs are with SPI, but you could put in one of the 16-pin interface, parallel port interface ones, and you could map it in to as an external device. Or you could put a larger memory because you want some sort of data logging thing, or you want a flash chip in there, or what have you. It has the ability to do all of that. Then there are some private areas for different peripherals, and then vendor specific. Up in the vendor specific, there are things like built into ROM, there's a bootloader. Now we use what's called ST-Link. We use this thing to go and program it. But in here, if you just bought one, just a chip by itself, it has on one of the serial ports the ability to bootload and be able to load code in that way. So it's right in the specific ROM. Okay, so here's this nice memory map view of where things kind of are. So our code's down at the bottom, our peripherals are up at this 40 million, there's static RAM. And so I want to just have a look at another picture from there. Let's have a look if I can find it. Oops, week 2. So this is zooming in. Remember I said it was at 40 million, the peripherals? So here's zoomed into just a section. There's 40 million, 5,000 to this kind of area. It says SPI 5, SPI 6. And we scroll up, GPIO-A is at 40020000 to 400203FF. So when we pass in GPIO-A or GPIO-D and it does something with it, it knows the base address. For instance, my LEDs, 40020C00, pass it port D, and it knows that then there's the mode, there's the input output, there's the speed based on that address. It's because it's all in this memory map, so it knows where everything is. So port A, the very first register after that is mode. Port B, the very first address is the registers for mode in there. Same with port C and so on. Okay. So that's how all of that comes together. So this is in that large data sheet, the RM0090, the 1800 page one, and it gives you where all the addresses of this are. Now, when we go and use our development environment, it knows where all that stuff is. So if I go and look, we can actually go and search for where port D is, and it'll come up with saying, when I go and try and get data out to LEDs or something like that, it knows it's at 40020C00 and something. Okay, so we looked before at the setup of all of that, and we looked at speed and everything else. And then when you continue on, I just wanted to go over a couple of others. So we said pull-ups and pull-downs and all of that, and we put it all together. So that's on the setup. We also need an ability to put stuff out and to bring stuff in, and so there's an input and output registers associated with each of those base addresses just after all of that setup stuff. I'll come back to that. So here's the input data register. Base address, offset of hex 10. So it keeps going up, and that's the input address. And again, 16 bits, the uppers are reserved because I have a 16-bit port, so that's all I had for that. And it says, okay, these bits are read-only and can be accessed in Word mode only. They contain the input value of the I/O port. So I can read base address plus an offset of hex 10, and whatever's on the pins gets brought in. Okay, and then same with output data register, and that's at offset 14, so 4 bytes more. I will be able to see the data that gets written out. Now, if I put data at that port, it gets sent out to the pins, as long as we're in output mode. You have to set up the configuration to say your outputs, as long as you are set for outputs, whatever you write in here shows up. Okay, and so it says output data register, read and written. For atomic bit set reset, the output data registers can be individually set or reset by writing to a GPIOX bit set reset register. So what it's saying is when I go and write out to there, your data is going to show up. But in between, with PIC, did you look at the read, modify, write? When you go and write something to a port, it actually reads the port in, modifies the bits, and writes it back out? Something sort of like that. It does the same kind of thing. And it's saying, okay, if you don't want something to be interrupted in the middle of a read, modify it and write it out, you can use this other register, bit set reset register, to do that kind of information. And so that one is kind of an interesting one. It's at address 18, again, base address plus whatever the offset is. And so here it's 32 bits, and it says bits 31 to 16. These bits are write only. 0 is no action, and 1 resets the output bit. So if I write up here, if I write a 0, it does nothing. If I write a 1, it clears that corresponding bit. If I write a 1, it clears the corresponding bit. What does it say about the lower bits of this? It says these bits are write only, 0, no action, and 1 sets the bit. So if I write a 1 here, it sets bit 15 of whatever port. If I write a 1 here, it clears that bit. So, and the reason they have this one is it's done in one shot, can't be interrupted. Okay? And so you might see some of the APIs used. Yeah?
Sorry, is the address offset, is that just assumed as soon as you type in GPIO?
Yeah. If you actually, and we'll highlight some of the functions and you'll see it actually goes and does it. So when you go HAL GPIO write, it's calling this stuff. Okay, and so you could go and write those individually, but it's doing that, and we can actually go in and see it. So my part of going over these, if you go, what the heck is that register? Well, that's what's going on, and it's a little weird in that I write ones to clear stuff on the upper 16 bits, and I write ones to set stuff on the lower. So it's kind of like, yeah, that's an interesting thing. Now it does say, oh, it doesn't. Did I put it in there? Oh yeah, there it is. What happens if you write a 1 there and a 1 there? Because one's set, one's clear. And it says, if both set and reset are set, set has priority. So if I try and set and clear the bit at the same time, then it's going to be set. Okay, and so it's an interesting register. Okay, the one other thing that's part of this document, and I've just fired in there, ST website has some example programs for the discovery board, and included in these are the STM32F4 discovery.cnh files, and these files provide a layer of abstraction from the CMSIS, which HAL is a layer on top of as well, and they just had some different structures, and instead of calling them blue LEDs and red LEDs and all of that, they call them LED 4, 3, 5, 6, whatever's on the board, and so they have some different structures. The only reason I mention it is you might see some example code if you're going to look around and it's not calling your HAL GPIO writes and stuff like that. And if you go and try and compile it, it'll go, I don't know what you're talking about. In the downloaded files, there is a discovery.cnh file, and it could be using these. It was before they did the HAL API, and just to put another layer on top of the CMSIS. And there are some examples that are out there that use it. And if you go and compile, and it might say, I don't know what STM eval led init is, and it's because there's these two files that you would need to include in your project. Okay, and that's why I mentioned those ones. Now, I want to go and talk very briefly just about Lab C, and then we'll go up to setting up our clocks and our debug information. So this week's lab is ADC polling single conversion mode. In your ESAT 130 Kuman kit, there should be a thermistor, okay? And it looks like this guy. I think some of them I might have even seen 4 pins. You'll have 3 or 4 pins, but it's probably this one. Now, a thermistor is usually a bimetallic something with a little coating on the top, and it's going to respond to temperature changes. And we can, usually not linear, there's usually a graph that you would be able to extrapolate your information from. They're cheap, and they're put in all sorts of things. In fact, if you have a 3D printer, there'll be a little thermistor right tied to the hot end. They handle temperatures very well, And so we want to have a look at the one that's in the Kuman kit. And so I want you to make a new project. But up till now, what you have done is you've made a project, and then hopefully lab 2, you've just copied the project and then deleted the things that didn't quite make it and renamed them appropriately, and then had your program all up and going again. Well, this time I want you to use the board selector option when you go through. You use the part, you use the actual chip, and the development environment knows what the chips are, but it also knows what a lot of the boards are. And when I go through, instead of having the part, I'll go through and select the board. I'll show it to you in greater detail coming up here. When I select the board, it knows what all of the other stuff is that's on board. It knows that there's an accelerometer on there. It knows that you have the LEDs on there. It knows all of that kind of information. And so it will initialize, and it knows the clocks. It knows that it's at 168 megahertz, all of that kind of stuff. So you will see a lot busier chip when we go in and set that up. And the reason I didn't do that to begin with is I wanted you to see a nice clear chip and not a lot of code. Because one of the things it'll ask you is, do you want to initialize all peripherals? And I want you to say yes. So it says, I have the board, set up everything that's on the board so it works right, and then we're going to put our stuff alongside it. It's going to put a lot of code in there that I don't necessarily need, and I could pair out. And if I was going to just use the chip by itself, I wouldn't do that. But I would want to look at the board, look at what's available, and then when I go to stick a TFT, for instance, I want to pick a place that's not being used. Okay, and we can look at that in the data sheets as well, but this is going to set all that up. So when we go and do that, like I say, it gets a lot busier. So again, it's board selector instead of CPU selector, and this time it's the STM32F407 disk 1 is the name of it. And when it'll go through and you say initialize all peripherals, and then it's quite a bit busier. There's quite a lot more code generated. And they called, I think they called them LED 6 and all of this kind of thing. So that shows a whole bunch of different things interfaced. And write a program to configure ADC3 to continuously read the thermistor in single conversion mode, display its ADC value in decimal and its representative temperature to 1 decimal place to the SWV ITM data console, and then upload a screenshot of your debug workspace showing the thermistor raw values and equivalent temperature outputs to D2L week 3 assignments by the start of lab 4. Upload a short demo of your lab showing the temperature change. So when I hold a thermistor, you should see the temperature going up, and let go, and you should see the temperature going down. Awesome. Everybody good with that? Everybody know how to start? How do we start? Well, new project, yeah. ADC3, so there's 2 things. Anything else? Let me see if I can zoom in here. Yeah, what's that? How would I find that out? A data sheet. Yeah, yeah, Google. Okay, so a couple of good things here is that, let me go to the things that are pushed up in week 3. I'm going to just look at this is from the pack that came with the Kuman kit on that little CD-ROM that was in there, and it's just showing me the thermistor, and it's showing me how to hook it up. And so it says that I have a 3.3 volts, and there's a little minus there showing the ground. And then there's the 3.3 volts, and then that says S for sense, so that's going to one of your analog inputs. Okay, and then so that's how I wire it up. If I look at the actual thermistor, this again was just going on that CD-ROM, and they had named actually they had named the unit. See, it says MF52D-104 whatever. The actual data sheet that they pointed to was known as a 103, but I'm pretty sure yours is a 104. And we'll talk about that. So it says M52 series bead temperature thermistor is made of new materials, new technology, small epoxy resin coated NTC thermistor has the advantage of high precision, fast response, and again, they're cheap. So one of the things there is a negative temperature coefficient, the NTC one. So as it gets hotter, the value of the resistance goes down. Okay, and so and again used in like hot ends on a 3D printer, among other things. So this top says it's an M52D, and so there's an M52D, and going to tell me. Okay, so M52 is an epoxy-coated M52 thermistor. And let's see, number 2 says model D is a PVC insulation. So we're M52D, so it's PVC on the little bulb end that you're going to get. And then it says resistance, 3 resistance at 25 degrees C, and we are a 104. It gave you the data sheet for a 103, but when I'm measuring across it, it's a 104. And we'll check yours in the lab to make sure, but I'm pretty sure. So it's 100K is what it should be. And then number 4, resistance tolerance. So it was an F, so it's plus or minus 1%. And then number 5 is a beta value. And way up top it says 3950. So we are a 3950 as our beta value. And all that'll make sense when we, the very first thing I want you to do is just get some values out of the A to D. And so what we're going to do is we have our A to D, we're going to read some values. It's going to give us something in the range of 0 to 4095, and I'm going to print it out. And then we can do something with it after that. Okay, that's the first thing. How do I do that? How do I read the A to D value? How would I find that? If I say read the A to D value in the lab, how do you know how to do that?
HAL GPIO read.
HAL GPIO something, or HAL something anyway, so I like that. So let's go to HAL, and if I go to contents, so that's that 1800 page manual. There's an ADC, you're looking for just a generic driver, and so there it is there. And then so it says, okay, HAL ADC. If I scroll down, has a whole bunch of stuff here, different channel outputs, different fields. It says, okay, we can be 12, 10, 8, or 6-bit. So in the ADC, I could want faster. There's so much per bit that you could get in resolution. So I could give up some resolution for making my conversions happen faster. Or I can go all the way up to 12-bit. Do you know on the PIC, what did you guys have? Was it a 10-bit, an 8-bit? What did you go up to as far as, was it 1020? 1024 or something like that? Okay, and so we're 10, so this is going to give us a 12-bit. Okay, so you had a 10-bit, so that's, and then it says interrupt generation, so we can get interrupts, single and continuous conversion modes. I'm going to talk about all of this coming up. External trigger, dual, triple mode on devices with 2. you can daisy chain these. You can get a conversion, and this your board has 3 ADCs, and I could chain them up. So the moment one gets a sample and starts a conversion, the other one does on exactly the same channel, and get 3 interleaving in a row if you want. Or you can have 3 doing different things. There's also what's known as DMA, and so I can set this up and have it do conversions and then do everything in behind the scenes, and we're going to look at some of those kind of things as well. It says how to use the driver. So that's kind of what I want to find out. And so it says initialize the ADC low-level resources by implementing HAL ADC MSP init, enable the interface, so enable a clock, enable ADC GPIOs, configure the ADC pins. In case of multiple interrupts, use start IT, configure the ADC interrupt priority, all of this in case of DMA, do other things. So it has a whole bunch of stuff. The graphical interface, as soon as you select the pin you want and say it's an ADC on ADC3, sets all that stuff up for you. Okay, generates a bunch of the code. You can go look at it. It's doing all of this stuff. It's going to call HAL ADC MSP init and do a bunch of initialization and say, there's an ADC set up. You said it was 12-bit. It's 12-bit. I don't know what you want to do with it. Won't do anything else. Okay, so, but it'll initialize it. And then we need to scroll on down a little bit. And there are ways of using it. Now, we are going to do ADCs over a few labs. We're going to do ADC with polling. We're going to do ADCs with interrupt, and we're going to do ADCs with DMA. Week 3, we're going to do it just polling. So I'm going to want to start a conversion. Did you do it with Wayne, ADCs with Wayne? Maybe. Start a conversion, wait for it to be done, read it. Okay? And so polling mode, start the ADC using HAL ADC start. So there's your HAL stuff, HAL ADC start. Wait for the conversion by calling HAL ADC poll for conversion. So it's a flag. And when the conversion's done, the flag is going to be set. At this stage, the user can specify what to do. To read the ADC converted values, you call HAL ADC get value. So again, that's in this, you'll be able to see how that's done. And then stop. Now, if I only wanted to do one, then I would call stop. If I'm just in a while one loop and keep going through, and every time through the loop I'll do another conversion, I don't have to stop it and keep starting it. If I was battery powered and I wanted to do a reading and then go away, I would stop it, turn everything off that you're not using. So I don't need to do this one unless I'm reading one thing and going away for a while. Okay, if I'm just continuously reading, just skip that step. Okay, so that's what you have to do to read the value. And so once you set up with the graphical environment, the thermistor, hook it up to your 3 volts ground, and your, I think PC0 is what I ask you to put it on, then set it up for ADC3. It initializes all of that. And then in your code, once it's generated, you call start, poll for conversion. As soon as the conversion's done, get value, and then go back through the loop. And then we need to print it out in some kind of way. Okay. Oops, where is it here? This is some, the document is setting up clocks and debug. It's in your week 2 information. There's a system known as a serial wire viewer in the development environment. And in the debug window, we can turn on the serial wire viewer. So how this is done, so you've compiled, there's no errors. Okay, you can look at and do this on the GPIO, for instance. When I look at the different configurations, under it'll default to main. Under the debugger window, scrolling down, there's this thing known as serial wire viewer. And you have to enable that to let the back channel to print out some of the variables that you want to show up, okay? One of the things about this is the core clock. It just picks, I think it says 16 megahertz or something. This has to be whatever your core clock frequency is, and it's 168 megahertz for what we're doing right now. If you changed it to 84 or what have you, that has to match if you want the information to flow out of it, okay? And so you enable a serial wire viewer, and again, this is all posted in week 2's stuff. You set it up for 168 meg. Okay, there's also a window called our setup for our serial wire trace, and you have to configure that. And there is a window that says it'll have the address 0 by default. It wants your variable. That has to be a global variable so it doesn't keep going out of scope. So for instance, I can put something in there and get data to show up for it, okay? And so I want to just go over to, if I can, the IDE. I have count, and that was, you had the count for going clockwise and counterclockwise in GPIO. So I moved my count up to user code above my main, user code begin private variable. So I put it there. And again, normally we don't want globals, but if you want to do some of this debug and get some of that information, you need to do that so it can see it in scope all the time. Okay, so I have that. And other than that, that's all I have done. Nothing is different from before. When I go to my debug and I'm going to go debug configurations. This is GPIO. And it defaults over to main. You see it says GPIO. I want to make sure I'm working on the same one. If I go over to debugger and we scroll down, if I can make it do that, okay, then you see serial wire viewer. And if I enable that and make sure this is matching my core clock frequency that's over in the clocks, which is 168 megahertz, then I've set that part up for having data go through into a debug window. Oops, that's where I guess I gotta plug this guy in. Okay, so I'm gonna go again. We'll go debug. Okay. This is, I'm just going to delete this. This is a data trace. You probably have something like this. Under Window, we go Show View. Under SWV, there's a few things. And there's Data Trace and Data Console. Right now, I'll pick Trace. I'm also going to want a console down the road, but Trace will work to begin with. So here's my data trace. Sometimes this is kind of stuffed into each other so you can't see some of the data. I'm looking for data coming up here. Now, the first thing we need to do when we go and configure this is there's a little tool set right here, Configure Trace. So I'm going to click on it, and it brings up that window I talked to you about. Now, the variable will show that it is 0x00. I need to enable it and have the name of my variable that was global. And so I called it count. Okay. This I turned on for the console mode. It doesn't need to be there right now, but this needs to match whatever your variable was or the address if you knew where the address of it was in memory. But typically global, just give the name of it. Now this is the part I always screw up because you've set that up, but every time you go into debug, by default it's all turned off. You have to turn this little record thing on to start the tracing. And it'll be off the next time you go in. So I'm always running the simulation and it's not working. Okay. And then we just go here and we go resume. And there's your count values as it grabs data. It just looks and says, what's the value? What's the value? What's the value? And goes through a back channel to set all of that up. So it's a way of, while it's running, I'm not single stepping through the code. If I went, paused here, and you could see, highlight, where is it? Over main.c, for instance. Now that I'm paused, if I highlight over any, where is it here? If I highlight over any variable, it's going to tell me what the current value is. So you can do that when it's paused and then run. But this will do it as it's running. Now, we are going and calling counterclockwise or clockwise or so on, and there's some delays in there. It's easy for you to fire out of the back channel far more information than it can display appropriately, and it'll start to give you some errors in the display, and it means you're overflowing it. It can't keep up with the amount of data you're asking. So usually have a delay of some sort. Don't just pump it at as fast a speed as you can get. Okay, so that was that part of it. Now, if I go back to that document, so that's this that I showed you. And again, you need to make sure it says that it's in scope by making it global. Okay, if I had it just local, it would show data and then not show data, and it gets kind of confusing. Okay. Next thing I want to do is redirect printf. So you want a little bit more formatted data, for instance. And so I can redirect printf. Now, oftentimes they will make a print function, and then the print function calls a put character function, and the put character function is empty because they don't know how you are possibly going to do it on a micro. Sometimes you can redirect that by putting it out a serial port, or in this case, we're going to put it out this kind of back channel. And if I look in syscalls.c, there's this IO put character when you call the write function. So print calls the write function. Okay, and so I want to go over to my IDE again and look at. Let me just stop that. And we'll go get rid of that. And if I go and look at some of the different files, there is a syscalls. And in syscalls, there is going to be the write function, which calls, there's a get function or a read function calling get character, and there's a write function calling put character. If you go to the very top, it says put character is external, and it's defined as weak. In other words, I defined a placeholder. If you want to use it, you need to define it. Okay, they just said we're going to have IO write calls put character. I don't know what it is. Okay, so what you do is you take put character here and you go put it. Where's a good place to put some of your functions in main? You put it down. Our user defined, our user begin and end for. So if I go there, now when I go and compile, I want to put something there. And you put ITM, and it's in that document, so don't worry about ITM sendcar, oops, not that one. How to do that one? ITM. Okay. So, and we'll return, because it's got an int. Oh, did I not copy my int? I forgot the int. Returns an int, so we need to make sure it returns the int. Okay, and usually when you return 0 from a function, it tells you that there was no errors, that everything was good. If you return a negative number, it's usually to tell whatever program called the function that there was some sort of issue. So returning 0 says everything's good. So now that's going to send out characters down this instruction trace macro cell backend. And so if I go back to this here, so I'm just telling you how to do that just here, do ITM send character. And the other thing that we need to do now is it's got a little bit more data going through. And so we need to enable a third pin. And the selection under system is trace asynchronous. And what it does is it configures the 3 pins to allow back channel data to go through. Okay. And so once again, we can't overflow it, but then by default, it's going to go out this stimulus port 0. So I just need to check that one off. I didn't need to do it for this, but I did need to do it for that. Okay. And if you select that, then when I have in my code, for instance, I printf, then it's going to print out. And it's going to be this time on that console instead of the trace window that we have here. It will be under, let me just go back into it. Oh, I messed up. Oh, it's, what have I got? Thank you. Okay, so the window for this one is again, window, I show view under SWVs. This is the data console. Okay, so that's where data is going to, and we can stuff it down there with all the rest of them down in here. And so that's where all your printf is going to come out of. Okay, now once again, when I go over to this, you know, we have our count and all that. It's this checked off as 0 that's going to make it work. Okay, and it's going to print it out there. The other thing is, there's 2 other things, and we'll talk about one next day. We need to enable floats. Remember how you had a special thing to do with in 130? Well, it's just a checkbox in the IDE. We just have to go and check that off. I've pointed out where it is in there. Otherwise, it'll print out everything fine, just not floats. But you need to put a /n. It will keep it till the buffer fills and then dump it out at erratic times. If you put a /n, it forces it to print out. Okay, so if you just printed out hello, you wouldn't see it probably. But if you go hello /n, you'll see hello, 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 and that kind of thing. Okay, so that's our. I've asked in this lab for you to print the output from your thermistor out to the console. That's how you do it. Okay, we have more to talk about. I'm hoping at least at the by the lab time you can get something out of the A to D and be printing a raw value, and we'll look how to turn it into a temperature next class.